Okay, so here's what I want to do as an introductory task. I'd like to do maybe two of these with you guys, and I'd like you to try the rest by yourselves. Here's our goal for the day. We want to now start to try to draw a stereochemical drawing for these molecules. I actually sent them to the printer if you want to grab them. Yeah, like the photocopier one. Sweet, thanks. So let's walk through a couple examples here. Our goal is to be able to draw them in 3 dimensions, and eventually, like probably after today, I want to make sure you guys get a copy of this software. It's very useful. All you got to do is just type in the name of a molecule, like say you want to have a ammonia, then it'll draw it for you as a 3D rendering, so that then you can use the mouse and rotate it around. You know what I'm saying? But if you don't have access to software like this, then we need another way of being able to draw them. So let's give it a try. What's the formula for ammonia? Okay, so think of it like Keynesian and Cami with puzzle pieces. You need one N, and you need 3 hydrogens. And then in terms of like the way these Lego pieces fit together, there's 5 valence electrons on sodium, nitrogen, 1 valence electron each on hydrogen. And then, I mean, honestly, I don't mean to be rude here, but like, I'm pretty sure my daughter can figure this out, right? Like, the one hydrogen's going to go there, the other hydrogen's going to go here, the third hydrogen's going to go there. And if I were to draw this a little bit neater in like the middle here so you can all see it, there, it looks like it's all pieced together. And this, I think, helps explain why there's such a thing as an NH3, but not an NH5, or not an N2H7. You know what I'm saying here? Like, you can visibly see, hopefully, now why this molecule is logical. So next issue, though, I need to try to figure out what this is going to look like in 3 dimensions. And yesterday when you guys got to play, I really hope that, like, tangibly seeing all the different molecules, you could see the issue of that this is flat, right? But in 3D, it's got to go, like, in spread out as far as possible. Does anybody remember the name for that theory, by the way, as to how the electrons spread out? There's an acronym, 5 letters. You sound like you're close. It's VESPER. It's valence, shell, electron, pair, repulsion theory. Basically, the idea is things have to spread out as far as geometrically possible. It's been a while since I took chemistry in university, but I believe in 3 dimensions, they want all of the angles to be about 104.9 degrees, and that's like when everything's spread out as much as you possibly can get it. So if I were to try to show this one right here, here's how I do it stereochemically. I would probably draw it like this: nitrogen going off to the corner like this to hydrogen, and then in an upwards direction, we would maybe we would draw the lone pair. Sometimes we don't draw lone pairs, and that would be in like a top orbital. I can't remember the exact number, but I want to think it's 104.9. That's sticking in my head. But like, that's how many degrees there would be between here and here. But you'd also need to have a hydrogen coming out of the page, and we use like a thick line to describe that. And same thing, if we were to measure the angle, there'd be like about 105 degrees from here to here as well. And then we use a dashed line to describe one going back into the page. And this is then an ammonia, which is spread out as much as it possibly can in 3 dimensions. Does that make sense? Okay. I'll try one more, then I want you guys to try a few here. Try to give you methane. Again, I mean, just think of Lego building blocks, right? So first, what is methane supposed to be made of? CH4. Okay, so I need 1 carbon and 4 hydrogens. And again, hopefully you guys don't think I'm rude here, but like, honestly, this is like piecing stuff together like a little kid, right? So hopefully this makes sense as to why we have CH4, not CH5, right? Why does a CH5 not exist? Well, because there's literally a spot right here, a spot here, a spot here, and a spot here for all the hydrogens to go. Right? So, I mean, now does this make sense why CH3 is not a valid molecule and why CH5 is not valid? Right? Like you can see it hopefully. So, okay, last thing. What kind of shape is this going to have? Do you guys remember the name for this one? Yeah, it's tetrahedral. By the way, I didn't mention it. What was the shape for the last one? Do you guys remember its name? Yep. Its official name is trigonal pyramidal. Yeah. Sometimes you can have trigonal planar, which goes in 3 directions and is flat. Those usually have a double bond in it. But if it goes in 3 directions and has a lone pair, it's trigonal pyramid. Okay. Anyways, this one's tetrahedral. This is a very classic one. Go up with one, go down to the corner with one, come out with one. Like this. Oh my goodness, I can't draw today. And have this one go back into the page with one. And if you can kind of envision this, it's kind of like the tripod on the bottom, only rather than an electron on the top, you have a hydrogen on top. Does this seem like something you guys can handle? Or can eventually handle with practice, maybe? Okay. Try the last 3 then. So I've done 2. Why don't I give you guys a chance to try some without me doing them first? So for the most part, for these last 3 days, I've just been doing everything. Take a stab at it. For some kids, it's actually kind of fun. Some kids enjoy doing this. Did you guys enjoy playing with the model kits yesterday? If you're like a creative, like putting things together kind of person, you're very visually spatial. There's no math in this unit. You know what I'm saying? No, this is it's more tangible, geometric. Look at that. Okay, that's what water looks like as a Lewis diagram. If you haven't got that far, water pieces together fairly easily. What sort of shape does water have, though? Do you guys remember its name? Angular or V-shaped or bent are all considered acceptable, but it's not linear. The reason why is these lone pairs right here. What ends up happening is you need H going to O, going to H. What ends up happening is these lone pairs right here kind of take up space. In a way, if I had to draw this better, maybe it would look something like this. You'd have H going down to O, over to H over here, but one pair of lone pairs needs to come out of the page, and the other pair of lone pairs needs to go like into the page. Does that make sense? Like you still have to go 4 directions, right? Because around the oxygen you have a hydrogen going one way, another hydrogen going the other way, but then these 2 sets of lone pairs, they also require space. So you could draw it like this. You could draw it like, let's see, H up could be the lone pair. You could have the hydrogen going this way. You could have a hydrogen coming out of the page towards you, and your last lone pair could be going into the page. You kind of get what I'm saying here is like you can rotate this any which way you like. At the end of the day, though, the important thing to know is that water has this bend shape where there's an angle in here. I actually think I threw this on one of your trigonometry tests. I'm trying to find the angle in water. I guess in 20 level, did I put one of those on a test? On a trig assignment? Anyways, if you guys can kind of see it, there's almost trigonometry in here where there's an angle between these 2 bent H's in the molecule. So, anyways, did that one make sense to everybody here? Hopefully I had a chance to try it first. I'll give you another few minutes to try carbon dioxide and nitrate before I jump in. Pretty sure I showed you carbon dioxide in our notes earlier. Here's carbon. Here's one oxygen. Here's a second oxygen. Again, honestly, think like a 5-year-old. Piece it together as logically as you possibly can imagine. If I could pause for a second on that thought, though, what's one of the biggest issues with us actually knowing for sure what this actually looks like? Bonds are made of electrons. Can we actually know where electrons are? No. So most of this is honestly just based on logical intuition and reasoning. It's based on whatever makes the most logical sense. You know what I'm saying here? So just use your best logic. Well, why don't we bond these two? Let's bond these two. Okay, there's a single electron here, 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 and here. You guys remember what we did to solve this problem? What do you call it? Yeah, make a double bond. So make this one and this one link up. Let's call it a double bond there. And make this one and this one link up. That's a double bond here. What kind of shape does this have now, though? What do you call it, though? Do you remember the name for it officially? It is flat. I agree with that. The name is linear because it literally is going in one big flat line. So you have oxygen to carbon to oxygen. You may or may not draw those lone pairs on the outside of the oxygen. You guys might notice, by the way, did you see how I didn't even think of this until after I did it, how instinctively I put these kind of on an angle? You guys see how I did that there? Originally when I drew them, I put the lone pairs on the top. And then when I redrew it the second time, I kind of put them on an angle. The reason why is that they would want to spread out as much as possible. So what would end up happening is you'd have a bond coming in on one side of the oxygen. Then you'd want to have a lone pair kind of going that direction and a lone pair going that direction. Can you see how that would be the most optimal way of spreading them out? So sometimes I just intuitively do that because I've been trained to. So if you ever see me do that where they kind of look like they're on an angle, that's the reason why. If you drew it like this, though, where they were on say the top and the bottom, that's fine too. Any issues with that one? Okay, this is the last one. Nitrate. What's different about doing an ion? Yeah, you have that extra electron due to its charge. Nitrate is an NO3, but you don't piece it together in the same way because the only reason this exists is because there's an extra negative electron on it. So if I were to do this one here, the best way I found to explain this one is say that nitrogen has 5 valence electrons, oxygen has 6, but you need 3 of them, so that's 18. And then there is 1 extra electron due to its charge. If you ever wondered why does nitrate have a 1 minus charge, well, it needs 1 more electron for it to be stably held together. If you give it 2 extra electrons, it's not going to work. So some things need a 1 minus charge, some things need a 3 minus charge. At the end of the day, what does that make? 24 electrons total? Okay, so let's start piecing it together. Nitrogen's going to go in the middle. We'll give 8 to it. I'll throw an oxygen here. What am I up to now? 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I believe I've now used all of my electrons, but I got a problem. What's my problem here? Can you guys see it? If you haven't gotten this far yet. Yeah, I ran out of electrons. Right? I believe I've used all 24 of my electrons, and yours may look slightly differently than mine, but hopefully if you can kind of rearrange it geometrically in your head, you'll see the exact same problem. Giselle pointed it out right here. This oxygen right here is missing some electrons. So you might wonder, well, why is it a nitrate minus 1? Why is it not a nitrate minus 3? Right? Why don't we just make it a 3 negative charge and give it 2 more electrons? Well, because there's other things we can do to manipulate it and make it work. Anybody know what the solution to this puzzle is? How do we get this thing to still fit the octet rule with only 24 electrons to work with? Yeah. See this lone pair that's sitting up here? Let's ditch that lone pair right there. And let's make it a double bond in this spot here instead. I believe I've still used 24 electrons. But rather than having these 2 electrons here be exclusively nitrogens, I'm going to use them a lot today. Kinsey and Cami are either sharing or not sharing things. If those 2 electrons are up here, those are just nitrogens. That's like when we buy a toy for Cami at Christmas and say, this is just for Cameron. Kinsey, you can't steal it from her. Does that make sense? But now what we've done here is rather than have those electrons be just nitrogens, right here I've shoved them into here instead and said, okay, you guys are now sharing this Christmas present. So both of you get to use those electrons. So now what ends up happening is I have a double bond here, and a single bond everywhere else. Let's count them up. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. But does everybody have access to 8 electrons now? Yeah, everybody's still got 8. You've got 8, you've got 8, you've got 8, you've got 8. Last question. What's the name of this shape? Try it. That's right, it's trigonal planar. The reason why for this particular one here is that if I were to draw it, this nitrogen is going in 1, 2, 3 directions. Okay. See how there's a double bond instead of a lone pair? But a double bond doesn't take up like twice as much space. I know when we draw it with 2 lines. But remember, what do those 2 lines really indicate? Okay, how big are electrons? Not that massive in terms of space, right? So it just means that in this little area right here, you have 4 electrons rather than 2, but you're still going effectively in 1, 2, 3 directions, as opposed to, can I redraw the trigonal pyramid real quick? When you drew ammonia, you had to go in 1, 2, 3, 4 directions, because that lone pair counts as the 4th direction. Do you guys see the difference here? Because there was a lone pair in ammonia, it means that these guys right here aren't going to be flat across. But in this one right here, because there isn't that lone pair anymore there, this is now trigonal planar. So I'm hoping this actually does what I want it to. That was a nitrate ion, right? Hoping we get the nitrate planar shape. There we go. So can you guys see how it has that double bond we were looking for? A single bond to single bond here. But if I orientated this properly, I should be able to show you that this guy is perfectly flat. Does that make sense? But the exact same sort of thing for an ammonia. Come on. You can do it. Not gonna work. There we go. Here's the ammonia. The ammonia also goes in 3 directions, but can you guys see how this is not flat? All due to the presence of an extra lone pair. Okay. Ultimately, if I could, before I go on to the topic 4 of my notes here, I want to go back to the very, very first slide, the comic strip I showed you guys right here. It's silly, but I picked this purposefully because this really is the key to all of matter. It has to do with this. It's this bit right here. This chapter explains how each element has valence electrons, which determine how easy it is for something else to mix. Right? And that's really our goal here, is that based on those valence electrons, they can happen in multiple different ways. The valence electrons could be a lone pair. The valence electrons could actually have empty orbitals. That's possible. The valence electrons could have a bonding electron. The valence electrons could unequally share. Someone could like steal 1 electron from each other. Right? And based on how those electrons interact with each other, that's how we get solids, liquids, and gases. That's how all of our matter exists. Does that make sense, what I'm saying here? So really, if you were to say like, well, what are we studying in this unit? It all comes down to one thing. It's electrons. And that's what we're going to talk about today in our topic here is we're going to talk about polarity. And how as these electrons interact with each other in different ways, based on shape and based on electronegativity and based on a lot of different factors, this is what causes our matter to be as unique and varied as it is. Because honestly, our universe would be very boring if everything was solid. Or if everything was gas. But fortunately, we have this broad spectrum where some stuff is gas, some stuff is liquid, some stuff is solid. And because of that, I mean, life ensues. Right? If everything was solid, I don't think we'd actually have human life. We need to have like liquids. Like our bodies are what, 77% liquid? So our goal today here now is to start talking about how poles can be formed so that things can start sticking together. So I'm gonna do what I rarely do. I'm actually just gonna read off my slide here. Over the last couple of days, we've been learning about the role of electrons in bonding. Very specifically, we've been learning about valence electrons. The outside electrons, right? As those valence electrons make bonds, the way in which they make bonds really impacts the shape of the molecule, the polarity of the molecule we'll talk about today. So, quick summary so far. What if you have an ionic bond? What's happening there? Outright thievery. Kinsey has decided to take Cameron's toy, and now Melissa's going to have to punish her for it. Okay? Like, outright, someone has stolen someone else's electron. But if I were to talk more about what's happening at a molecular level, it has to do with electronegativity. One species really wants an electron, like say fluorine has an electronegativity of 4. Another species has a low electronegativity. It really doesn't need its electrons, like sodium. And someone literally just like steals it. Does that make sense? That forms an ionic bond. Do you guys recall the shape, the one shape you need to know for how ionic bonds form? What the name of it was? Go get breakfast. And then after that, I'll reveal the answer. Maybe you'll think of it while you get breakfast. I'll start drawing it. What's the name of the shape of this ionic pattern here? Not checkers. That would have been a good idea, though. Thank you, guys. All right, anybody remember what the name of the shape is yet? Daniel? That's it, yeah. You guys are going to want to know this, by the way, whenever we do a test. Crystal lattice. The idea here, basically, is that there is no sharing of electrons. This negative item right here, whatever it is, say chlorine, it has literally stolen sodium's electron. And this guy stole this guy's electron. And this guy stole this guy's electron. And you have this interlocking shape of positives and negatives. Do we need to really demonstrate a bond between them? And the answer is no. Because you know how when we sometimes draw molecules where it's like this with like a stick to this with a stick to this one? Remember how the stick represents electrons in the middle? Is there an electron in the middle of these two guys like this? I want to show you something unique actually. Let's say that I went to here and I asked you to type in a molecule that's clearly ionic. Let's just pick a simple one like sodium chloride. Where's the stick? We don't need one. Why? There's no gray area where the electrons are being shared. Whichever one is which, this guy right here is completely stolen this guy's electron right here. Okay. Now, why isn't it showing a whole bunch of them? Do you have an idea why it's not showing like a whole bunch of them? Why is there only 2 of them here? Yeah, it's giving us what's called the empirical formula. I showed you guys this yesterday. What ends up happening is there's 1 sodium to 1 chlorine. It's probably not like this. This would literally be just one of them. There's probably like 10,000 sodiums and 10,000 chlorines, all in this pattern right here. But it's just giving the lowest common number. Okay, so that's an ionic compound. Now, here's one of the issues, is that it's actually not that strong of a bond. Why? Anybody know? I've talked about this before. Why is an ionic bond actually very easy to break under the right conditions? How do you break an ionic bond? Dissociate it by adding. Yeah. So although it has, even though that ionic bonds are usually in a solid format, they're actually the ionic bonds within an ionic compound are actually easy to break. One other word you should know is the word electrostatic. I think I bolded that one in our notes the other day too. Electrostatic is the name we give to this sort of thing right here, where you have a negative attracted to a positive, which is attracted to a negative, which is a positive. So you should know that it has a crystal lattice shape, and it's held together electrostatically. For those of you guys who did my physics class last year, that word should hopefully kind of make sense, right? Because we worked with different point charges. Okay. The other thing we've talked about for review so far is covalent bonds. Covalent bonds share electrons, which means that they actually have a bit of a stronger bond. I cannot make water or carbon dioxide or methane dissociate in water. It's actually not possible, like an ionic bond is. But here's the weird thing. Covalent bonds are normally gases or liquids. And here's the reason why. What reason does, I'm just going to make a new one here. For what reason does this methane molecule right here have to be attracted to another methane molecule over here? Because really that's what makes things a solid versus a liquid or a gas. Why does this molecule attract this molecule? Or even does it? You know what I'm saying here? Because if these two molecules are attracted to each other, then you might have more of a tendency for there to be a liquid or a solid formed. But if there is no form of attraction between the two, then maybe that explains why they're in a gas form. You get what I'm saying here? So one of the vocabulary words I'm starting to introduce is the word intermolecular bond versus an intramolecular bond. And this is really the focus of my last topic of notes, but I want to introduce these words now. Do you guys remember from me saying this informally which one is which? What makes something an intramolecular bond? I'll do the second one first. It's a bond within the molecule. For example, like this thing right here is an intramolecular bond. It's a bond that keeps the inside of a molecule attached together. Okay. An intermolecular bond then would be this right here. It's what makes this molecule want to stick to this molecule. And this is the point of my lesson. I'm taking a long time to make my point, but hopefully I'm doing a good job. Today's topic is polarity. We're going to talk about how certain molecules have a pole to them. You guys know like poles on a magnet? There's north and south. Okay, and then magnets can then stick together. Molecules can sometimes do that. And if molecules can be considered polar, they can then have attractive forces that cause them to cling together. If they do that, they will then start to be more like liquids or solids. So here's the question. Is there any reason for this molecule here to attach this one here? And maybe you already know the answer to this one. What's the state of matter for methane? Methane's a gas. So is there any reason for these two molecules to stick together? No, there actually isn't. So let me show you over the next few slides. So let's move on here. When we're talking about molecules sharing electrons, I've already given this example before. Sometimes they share very nicely, but sometimes they're like my daughters who bicker. And when Kinsey and Cami are sharing, I'm using air quotes here, they're sharing really, how did Melissa phrase this last night? Kinsey would say, it's really mine, Cami, but you can use it right now. That's what she'd say. This is Kinsey's version of sharing. It's really mine, Cami, but you can play with it while I'm not. Okay. Well, that's really how some things share their electrons. Let me use an example here. Here's hydrogen fluoride. Can you guys find in your periodic tables the electronegativities for both fluorine and hydrogen? I'm pretty sure I know them both, but I'm a little rusty. Is it 4.0 and 2.2? 2.2. Okay. They're sharing, but I'm saying that very loosely because are they really sharing? No. If I were using my Kinsey-Cami example, really what's happening here is fluorine is saying, hydrogen, you can have my electrons, but only when I'm not using them. But I'm going to use them pretty much all the time. Does that make sense? And so what really happens here is if I were to kind of draw like a diagram right here, illustrating the probability of where the electron is at, somewhere in this little section right here, we know there's electrons, right? But this is supposed to be a picture kind of describing the fact that we believe that fluorine is taking them. So sometimes we draw a little arrow like this, indicating that fluorine is stealing them more often than not. Does that make sense? And we use this notation right here. It's the Greek symbol, I forget which one it is right now. It's a Greek letter, and it means slightly. So sometimes what we would do is we would put slightly negative on this side and slightly positive on this side, thereby indicating that this side of the molecule is taking the electrons just a little more often, and that means these guys right here have to be the positive ones left over. Now I want to make sure I'm really clear on something. This, however, is not an ionic bond, because in an ionic bond, the person steals the electron entirely and never gives it back. This is the scenario where Kinsey takes Cami's toy, but Melissa says, you can't have it. So she says, okay, fine, you can play with it a little bit. Does that make sense what I'm saying here? This isn't a complete transfer of electrons. Because what does a complete transfer of electrons look like? This. You get the difference there? They're still sharing, quote unquote, but they're just sharing them unevenly. And what it leads to then is a molecule that's slightly positive on one side and slightly negative on the other side. Now, I'm going to start drawing multiples of these now. So I'm going to draw HF again. Here's HF, but I'm going to say that this side right here is a little bit more negative, and this side right here is a little bit more positive. And I'm going to draw another HF, which is going to involve this guy being slightly positive, this guy being slightly negative. Is there a reason, any reason, for these two molecules then to become attracted to each other? And hopefully this makes sense here. You'd say, well, hang on. If this side here is slightly negative, and this side here is slightly positive, wouldn't these two things want to have a little bit of attraction to each other? Does that make sense? And let's say I brought in a third HF and I put it over here. Here's an HF like this. This hydrogen side is slightly positive. This fluorine side is slightly negative. Wouldn't this slightly negative and this slightly positive, wouldn't they want to start attracting to each other? Here's what this means then. Hydrogen fluoride is actually a liquid. If I were to tell you the state of matter for HF, it's usually in a liquid format because there's a reason for these molecules to stick together due to slight bond discrepancies. Does that make sense what I'm saying here? But let's go up in our sides a little bit here. The one I skipped here is H to H. Okay. Now imagine that Cammie's a little bit older. She's not 3 to 5, but like both of my girls are about equal in age. And they want to fight over a toy. But now in this example here, there's really no winner. Because what happens when a hydrogen fights with another hydrogen? Who wins? Well, nobody. Right? In this example here, they exactly evenly share the electrons. 100% even, because you're literally fighting against your identical twin. And so you know how in this diagram right here, this side over here was slightly larger because fluorine is going to steal the toy a little bit more than the other? Well, right here, it's exactly even. And so the slide I found on the internet basically says here that the dipole movement is 0 because there is no dipole. So this side right here is not slightly positive, and this side right here is not slightly negative. It's exactly neutral. Well, in this example right here, what reason does this hydrogen versus this hydrogen, is there any reason for these two things to be attracted to each other? No. What state of matter then is hydrogen gas? Gas. Yeah. And this helps to explain why in this one right here, H bonding with H is in gas form, but right here, H bonding with F is probably going to be in a liquid form. And we can now start to see reasons for why things are going to stick together. Right? If they don't stick together at all, they're probably a gas. If they have a reason to stick together a little bit, they're going to be a liquid. And if there's lots of reason for them to stick together, like say this bond right here, well, this thing right here is going to be a solid because it's entirely positive, negative, positive, negative. Does that make sense? Water is a great example of this. Water is a polar molecule. If you guys haven't ever seen this before, try an experiment at home. I don't actually have a comb nearby, but take a comb your hair, give it a bit of a charge, and then have some water just dripping from the sink and put the comb nearby. If you've never seen this before, you can actually make the water deflect. Anybody ever seen this magic trick before? The reason why is that this is a polar charged comb, and the water is also polar. And due to that, you can actually cause the water molecules to get pulled towards the comb. I want to show you that now with the water molecules we drew earlier. Remember how we drew water before? It went like this, H to O to H. This was roughly its shape. That bent shape to it. Okay. Let's talk about electronegativity. Who wins the electronegativity fight? I believe hydrogen we just said was 2.2, correct? Is oxygen 3.4? Okay. Well, now shape also matters, though. It's not just about who wins the fight, but it's also about the shape. In this molecule right here, what ends up happening, I'm going to use a highlighter to help differentiate this. Who wins the fight here between this hydrogen and oxygen? Well, oxygen does, which means I'm going to draw an arrow. We usually draw an arrow pointing towards this oxygen right here, meaning the electrons are going to spend slightly more time right here than they are over here. That same thing occurs right here. This hydrogen also loses the fight to oxygen. So I have 3 kids. This one right here is Kinsey, she's my oldest. This is Cameron, she's 3, and this is Cadence, who's 1. And in this example here, Kinsey is stealing both Cameron and Cadence's electrons. Okay? She's really being a bully here. What does that mean about this oxygen right here? Well, it means that I can say that it is slightly negative on this side. Because this oxygen right here is winning all of the electron fights, which means that this hydrogen over here and this hydrogen over here are become slightly positive. Does that make sense? Well, what happens if I draw an identical molecule to it? So give me a sec here. I'm going to cheat because I can. I'm going to select this entire thing. I'm going to group it together. I'm going to copy it, and I'm going to paste the second one. So now I have 2 of them. Let's say I put this molecule right about here. Is there a reason for these molecules to stick together? Yeah, hopefully you can see it. Is that right? Oh, I'll use a crayon here. Right here you have a slightly negative molecule. Right here you have a slightly positive molecule. These two things are going to want to attract to each other. In terms of terminology, then, I want to teach you this properly. Right here and right here, we call those intramolecular bonds. Those are bonds within a molecule. But right here, this attraction that causes this oxygen and this hydrogen to be attracted to each other, we call that an intermolecular bond. And it's what makes water stick together. Now, this makes sense to you guys because what state of matter is water? Possibly even solid, depending on if it's cold enough outside. Does that make sense? If I could, I'd like to do a very, very similar example, but show you a difference between one. We also did today carbon dioxide. I had you guys draw carbon dioxide, and it didn't have a bent shape, though. Carbon dioxide was flat. What state of matter is carbon dioxide? Well, hang on a sec. One of them involved just a two, like one in the middle and two on the outsides. But the bent one's a liquid. The flat one is a gas. Let's explain why. Carbon, okay, I know oxygen was 3.4. What's carbon, 2.6? 2.6? Now, if I were to do the exact same thing, who wins the fight? Well, what ends up happening, I'll use a crayon again, is that oxygen wins the fight. So we usually draw an arrow towards this side right here. And this oxygen also wins this fight. But here's the difference. This molecule is symmetrical. This molecule is symmetrical. And so what ends up happening is this one's getting pulled this way. This one's getting pulled this way. Imagine this were a big tug of war. What's going to happen to the carbon if someone pulls it this way and someone pulls this way with equal strength? The carbon is actually going to stay right in the middle, isn't it? If I get pulled equally on both sides, I know both sides are getting pulled, but really, due to symmetry, I should really change out of the crayon. This looks really kindergartenish. Due to symmetry, you have an equal amount of like pull, and based on this, although your molecule is getting pulled in both directions, what ends up happening is this is a non-polar molecule. I want to go back and show you hydrogen again, or show you water again. I should be able just to paste a new one on there, right? Paste. There we go. Here's that water molecule that I did earlier. Let's bring it down to the bottom. Here's water. Is this one symmetrical? Well, not in the same way. I know that I've got arrows pulling outwards here. These two arrows, though, are they pointing directly into each other? Well, no. Let me just do this as like a real-life analogy. Imagine that this is the thing I'm pushing on. If I pushed from both directions equally, is this thing going to move? No. But what happens if I came one in at an angle and one at an angle like this? Then is it going to move? You know what I'm saying here? Hey, guys. I'll file them. Do you guys understand what I'm saying, though? Is that because these ones are going exactly opposite each other, this is it's a symmetrical molecule. It means there's no pull to it. But on this molecule right here, because of the fact that like this one's going down at an angle here, this one's going down at an angle here, really there's like a net negative on this guy right here because they're like both getting pulled towards the bottom on that side. Does that make sense? For you guys that did physics with me, think vectors for physics. One vector is going this way, the other vector is going this way, so the net is going like this. You know what I'm saying? But in the other example, one is going this way and one is going this way. What's your net force on this one here? Nothing. There's no net force on this one because it's exactly symmetrical. This one right here, though, because they're at a bit of an angle, there is a net force when you're done. You've just drawn the molecule in 3 dimensions. So you'll know whether or not there's any sort of like symmetry to it or not based on the fact that you can now draw it in 3D. Does that make sense? I'll show you more examples then. Bear with me then. Minus that question there, because I know I can answer this in a bit here. Do you guys feel like you get the idea about whether molecules will stick together or not? If you can show there's a net dipole, they'll stick together. They'll be liquid versus gas. Why don't I hop forward here? Let's find some examples to do that. I'll come back to these slides. You skip right to the end. Honestly, I've covered everything I need to here. Let's find this one here. Oh shoot, it's carbon dioxide. We'll do carbon dioxide again, and then we'll do a new one. So the question here is, what's the bond polarity for carbon dioxide? So why don't we write this down officially now? How am I going to figure out whether carbon dioxide is polar or not? The first thing you're going to want to do is draw carbon dioxide. So we've already done this like 3 times today. Here's carbon dioxide. And it has a linear shape. Does that make sense? Because we've already done this twice today. Here's what you're going to then do. You're going to draw an arrow indicating who wins the fight for electrons. Who wins the carbon-oxygen fight? I think it was oxygen, right? Who wins this carbon-oxygen fight? Oxygen. Is there a net winner in this fight? Okay, due to this is a non-polar, linear molecule, which means if I had to guess whether it's a solid, liquid, or gas, it's going to be a gas, right? Because if there's no polarity to it, then why would this molecule want to stick to another one? Let me do all the examples first, then we'll look back. Let's try the next one. Let's try ammonia. We've already done ammonia today. So if you guys can remember how it looked, let's take it from the top though. Ammonia was NH3. By the way, do you guys know what state of matter ammonia is? It's a liquid. If you didn't know this, ammonia is a liquid. But let's show why it's a liquid now. Now we can explain why. Ammonia is going to be N like this, with 3 hydrogens off of the edges. So maybe this part will help answer your question, Naomi. We now have to draw this in 3 dimensions though. So when I try to draw ammonia in 3 dimensions, when we did this earlier, it looked like this. N over to H, out to H, backwards to H, with my lone pair on the top. So there's my ammonia. So if you're able to draw the stereochemical formula, the new thing that we're doing today now is let's talk about discrepancies between electronegativities. So think of it as a fight. Who's going to have the electrons more in this fight right here between nitrogen and hydrogen? Nitrogen? Okay. Well, because of that, I'm going to draw an arrow going this way. That's an arrow there. Well, that same logic applies to all of these bonds then, right? So this one right here is also going to get pointed towards the nitrogen. And this one right here is also going to get pointed towards the nitrogen. Wait, here's the really important question. Are these 3 arrows, are they going to even out in the end and have like a net force of 0? Or is there going to be a resultant when you're done, if I use those sort of like physics terms? Are they going to completely even out, or is there a resultant when you're done? What do you think? There is, yeah. What ends up happening here, let me use a manipulative here. I got 3 pens here. You have 1 bond, 2 bonds, 3 bonds, all like this as your tripod, right? This one is kind of going up a little bit. This one's going up a little bit. This one's going up a little bit. So when you're done, really, this guy right here, the nitrogen at the top, is kind of stealing all of the electrons. So in a way, what's going to end up happening is this nitrogen here is going to be the slightly negative side because everybody is pointing towards him. And then like the bottom side of the molecule here, maybe I should just draw it as like the bottom side entirely. This side right here is going to be the positive side because all of the electrons effectively are getting pulled like upwards. Can you kind of visualize that? So long story short, here's the question. Is there a polarity to ammonia? Yes, and if you can agree there's a polarity to ammonia, now we can explain why ammonia sticks to other ammonias and thereby makes it a liquid. Let me see what's on my next slide here. Oh, methanol. I still have stuff left here. You know what? Actually, can I add a slide? I can go off a book here. Let's do what's the one I just had in my mind? Water. Oh, let's do methane. Find bond polarity for methane. Let's do this one first. Off the top of your head, do you guys know what state of matter methane is going to be? Okay, here's the rationale then. Because it's a gas, we believe methane does not have any intermolecular forces keeping this methane and this one stuck together. Because if there was, methane would be a liquid, a solid. So when we're done, I believe we're going to have to prove that methane is not a polar molecule. Does that logic make sense? Yep. So let's prove it. First, I got to draw methane. Methane is CH4. By the way, this example right here is like the perfect example of what I would try to show you guys every day of the week. The first day we did stuff, I wanted to show you how to do a dot diagram. So if you guys can do the dot diagram for this, that was supposed to be like the first day I showed you stuff. Makes sense? The second day, then I showed you how to upgrade a dot diagram to a Lewis diagram. Oh, sorry, a Lewis diagram is what we started with. This is now a structural diagram. And then finally, we want to upgrade this now to a stereochemical diagram, which is now in 3 dimensions. And it would look like this. Day 1, dots. Day 2 and day 3, lines and 3D lines. This is topic 4 now. Let's figure out who wins all of these fights. So again, my daughters are fighting for playing with, well, right now it's Duplo. So they're fighting for Duplo. Who wins the fight between carbon and hydrogen? Carbon is 2.6, hydrogen's 2.2. So carbon wins this fight. But it also wins this fight, and also wins this fight, and also wins this fight. Everybody's pushing in towards carbon. Now, I know it's in 3 dimensions, but can you guys understand and visualize how, because everybody is equally pushing inwards, because of that, really there's like a net of 0. Does that make sense? Right? Like, this one's pushing down, but in a way, this one and this one and this one, they're all kind of partially pushing up. And this one's pushing right, but this guy's kind of pushing left to make up for it, right? So like everybody has a doppelganger on the opposite side that's kind of pushing the other way. So at the end of the day, this is a non-polar tetrahedral shape. And because of that, there is no polarity to it. So when we write CH4, we now know that CH4 should probably be a gas, because there's no reason for this CH4 to stick to other CH4s. That's my lesson, essentially. If you understand that, I'll go back and do all the slides I skipped, but that's basically what I'm trying to show you today. Naomi, does that better answer the question you asked? Okay. Well, let's try one you guys haven't done yet, because this is one that I haven't had you try yet. So everything up till now has been something that's been a bit of a review. Now let's give you a new challenge. I'm going to give you CH3OH. So here's my question, basically. Predict for me whether or not this molecule should be a solid, a liquid, or a gas. Do you guys remember what this is called, CH3OH? It's methanol. Do you guys know the state of matter of methanol? It's a liquid. Okay. We used methanol in our in a couple of our labs before. It's a liquid, and then we usually burn it because it's the stuff we use in the flame tests. So okay, so let's prove when we're done that after we've drawn this molecule that it should hopefully not be symmetrical. It should not be like, it should have a dipole to it. Okay. So let's draw it out here. First, I have to start at the very, very beginning, though. I need to do a Lewis dot diagram. So again, pretend that you're my daughter playing with Legos. We need a C. We then need 3 H's. 1, 2, 3 H's. Then we need an O. Then we need an H. And we've got to fit it together. This one's a little bit more challenging. Everybody okay so far with me making the Lego pieces, though? So this is like our first day of the unit. I think the logical thing to do here would be to take each of these hydrogens. Can I ungroup them? Ungroup. I'm going to take like this one here and rotate. That's not going to work so well. Group. There we go. And I'll put, like, say, one there. I'll take those guys, and I'll put it there. Does that kind of start for a logical sense? And now maybe you can see, well, this is why they write it as CH3OH. They don't write it as CH4O. Because let's say you took this last hydrogen right here and plopped it right there. How are you going to fit an oxygen in there now? Everybody's all filled up. So the only logical way for this to work now is for you to have CH3 right here, take your oxygen, plop it right there, and then have your hydrogen go last. Does this help to explain why we write CH3OH in that format? Like, it's been done to specifically help you know what order things fit in. Okay. So this is what we ideally learned our first day of the unit, how to draw a Lewis dot diagram. I didn't make you do one that's complicated, but with practice, I hope you guys can kind of piece it together like that. So that's step one. Step two, we're now going to upgrade from a Lewis dot diagram to a Kekulé structural formula. And literally the only thing that you do differently is you do this. You go a line in between them. This is like the most standard way we have of drawing a formula. You guys were doing biology with DNA the other day, right? Did lab show you some molecules where you do it like this with the line in between there? Okay. This is the most common way of drawing it just because it's super quick and easy. Sometimes we put lone pairs on there. We don't always, but sometimes we do. Then yesterday, I then wanted us to upgrade and learn how to upgrade this so that eventually we can draw it in 3 dimensions. And that's one of the more challenging things to do is to get it to a 3D rendering. Obviously, if you have the program, it'll do it for you. But, I mean, you guys need to be able to do it yourselves too, right? So here's how you do this then. You got to figure out which are the central molecules. And I actually put a plural on that on purpose. I said central molecules. This guy right here is a central molecule. But this one right here is also a central molecule. Okay. So I'm just going to pick one to start with. I'm going to start with this carbon right here. Now, in order to make this work, though, you know how I typically draw it like one up to, like, say here, one over to there, one out like this, and one like that? I'm going to shift this just slightly to make it easier to work with. So see whether this makes sense here. I'm going to change this. I'm going to go carbon going up to hydrogen still. But I'm going to go this way here and this way here for my 2 hydrogens right there. So I'm picking the up one as the top hydrogen, and these 2 guys right here are going to be the out and in versions. The reason why I'm doing that is that now this bond right here to oxygen can be a flat bond to oxygen. Can you see how I've just done a flipping 180 degree reflection? That's all. You can do that anytime you like, by the way. It doesn't really matter how you draw it because it's in 3 dimensions. Now let's focus on the oxygen shape. What sort of shape should this provide right here? Linear or bent? Bent is correct. The reason why is those lone pairs. If it was linear, it would go like carbon to oxygen, completely flat. But what are these lone pairs going to require? I'm just going to draw this little section right here. It's going to require like an X to a Y to a Z, but then you're going to need to have a spot for a lone pair and a spot for another lone pair because those lone pairs, they take up space. This is basically just like water right here. You know how water goes H, O, H? I know this isn't an H right here, but it's coming from here, going to O, going to H. But those lone pairs, they require space. So there needs to be a bent shape to this right here. So you can draw this in a lot of different ways. I'm going to draw it like this. I'm going to draw it back with a bend like this, back up here. And then if I wanted to draw the lone pairs, I could say that one set of lone pairs is now coming out of the page, and another set of lone pairs is going into the page. If you guys can see, this oxygen right here then still has 2 lines that are flush in the page itself, and then one coming out, one going in. And then this carbon right here has 2 lines that are flush with the page, one going out, one coming in. And so something like this should be what methanol looks like. Now, the more you do this, the better you'll get, because literally this is our unit, by the way, is draw a molecule, look at it, interpret it. Let's say you wanted to test it, though, because this is what you guys will start doing. Here's methanol. Okay. I know this is completely backwards now, but let me rearrange it and make it look normal. Can you guys see how I've made this go so that there's one that's kind of going up, one out and in on this side right here. So if I were to like, Compare them here. So this is the one I'm trying to compare to here. There you go. Can you see how there's one that's going up? That's this one right here, essentially. There's one that's going out and one that's going in. That's this one right here. There's a bond across. That's this one right here. And then the hydrogen, I drew it going up, but they drew it going down. So I should be able to fix this by just doing something more like that, I guess. It's not the nicest one I've ever done here. So, there. Here's one going up. That's effectively this guy back here, right? Here's one coming out towards us. That's this one right here. Here's one that's going back into the page. That's this one right here. Here's the bend to the oxygen right here, and the hydrogen coming up. What's in this space right down here? Two different lone pairs. Does that part make sense? Okay, now to answer the final question. Is this molecule completely symmetrical to the point where like everything is exactly even? The answer is no, but let's prove it. We'll do some electronegativity differences. I'll use a highlighter here. Who wins in the fight between a carbon and a hydrogen? Carbon, right? Okay, so I'm going to draw a line in towards carbon, a line in towards carbon, and a line in towards carbon. Okay, then who wins in the fight between carbon and oxygen? I think oxygen does, right? Oxygen is 3.6, so now we need a line that goes out this way. And then in the fight between oxygen and hydrogen, I believe oxygen wins that fight quite handily. There. Is this a completely symmetrically balanced molecule where if I were to ask you to find the net force, it would be equal to 0? No. Right? And usually you don't even need to do these lines anymore. Like after you've done a couple of these, hopefully you can just look at the molecule and say, that isn't symmetrical. Right? And because of that, there's going to be a dipole to this molecule. One side is going to be negative, one side is going to be positive. If I had to take a guess to it, I would suggest that due to both of these lines heavily leaning towards the oxygen, I would suggest that this side right here is probably the negative side, just because these guys are both pointing in here. These guys here more or less balance each other, almost. They're not perfectly balancing, but this one, and this one kind of balance each other. If there was a fourth one going in, it would have balanced, but there isn't a fourth line. So I imagine, though, that because this one and this one are pointing in, there's really a negative sign down here. There's probably a positive side up here. If I were then to take this molecule and put a second one near it, they would have valid reason to cling together. Hence the name of our lesson today, polarity. There is a pull to this. You guys have any questions right now? Okay, why don't I go back to the skipped notes, and then I'll show you what you guys can do to finish. Because I've more or less taught what I need to. That, I think, was the last slide probably, right? Yeah, that was the last slide. Let's go back through what I skipped. See if there's anything in there that's really relevant. Oh, yeah, it's a ton of pictures. That's right. Oh, okay. Why don't I start here? This is where I left off here. The picture of the oil and water. Have you guys seen a picture like this? I must have shown you this before, the idea of like oil and water. You know that oil and water don't mix. One of the reasons why is due to polarity. Water is polar, oil is nonpolar. And polar things can dissolve other polar things. Nonpolar things can dissolve other nonpolar things, but if you have one of each, they don't mix with each other. So water it must be a polar molecule. Oil must be a nonpolar molecule. And that's why they have literally a separation to them. You guys have seen this before, right? The poles then, in terms of like words I should use, why do these poles exist? It's due to electronegativity. As there's slight imbalances in fights over electrons, remember that comic strip again, right? The whole point to how bonds form is due to valence electrons. If valence electrons are being fought over, sometimes there's a complete winner. Someone literally steals it. Sometimes there's like a sharing, but it's like a Kinsey-Kami sharing. Sometimes there's actually equal sharing. Sometimes there's symmetry involved. And so depending on how that works depends on whether there's a pole formed. These pictures here more or less just kind of show the concept here, I guess. What you end up having here is that oxygen wins the fight for electrons slightly more, and hydrogen ends up becoming slightly positive. So what happens is this slightly negative right here can attract this slightly positive. This slightly positive can attract this slightly negative. Does that make this makes sense to you guys, right? I can skip over this. Here's another picture, I believe. This is hydrochloric acid. Do you guys remember the state of matter for hydrochloric acid typically? Liquid is usually, it's usually a liquid or an aqueous format. So here's why. In the fight between hydrogen and chlorine wins the fight, right? So what ends up happening is more of the electrons are on the chlorine side, less of them are on the hydrogen side. Well, here's a second one. Because of that, there is a force of attraction, and that vocabulary I need you guys to start picking up on is you call that an intermolecular force. This one right here is an intra, by the way. The bond within the hydrogen and chlorine is intra. The bond that makes these two other ones stick together, though, is inter. They're both between hydrogen and chlorine, though, right? This is between a hydrogen and chlorine. It's an intramolecular bond. This right here is also between a hydrogen and a chlorine, but it's an intermolecular bond within the molecule or outside of the molecule. And this is fundamentally how we believe matter works. Okay, here's the terminology I've already been using. We call these polar covalent bonds, okay? If there is that discrepancy, we call it a polar covalent bond. And it's what causes these things to stick together. So I don't think I need to do this slide all that much. It is possible, though, to have non-polar bonds. How do you have a non-polar bond? Well, what about something like, say, chlorine, Cl2? What happens if chlorine is engaged in a fight with another chlorine? Who wins? Nobody. This is like an eternal battle against your identical twin. This would be like Flash and the Reverse Flash, always fighting each other, never winning. Found a comic book reference here. You guys get the idea what I'm saying here, though? Is if chlorine fights another chlorine, who wins the fight? Nobody does. Which explains why chlorine is in a gas format often. Right? Because there's nobody to win this fight. But make it hydrogen and chlorine, and all of a sudden now there is a winner, and now it's going to be probably a liquid. Okay, this is a slide I should spend more time on, so find this one here. I've been describing this before, but now's a good time to summarize this. There is a spectrum, a continuum then, of bonding. Okay, kind of like you might have like an ideological perspective spectrum in your social studies class. You have the same thing in bonding. Okay, basically the way it works is that on the far end of the spectrum, we'll go over here on our left-hand side. You have ionic bonding. Ionic bonding then means that in terms of electronegativities, there is no fight. Cami just got her toy stolen. Okay, there is no sharing happening whatsoever. It's a complete theft. Okay, that's ionic bonding, and this takes place when the electronegativity difference is quite large. In general, the breaking point here is a difference of 1.7 or more. Okay? If the electronegativity difference is about 1.7 or more, usually that is enough for someone to literally just steal and thief away an electron. Okay? And they're not sharing it at all anymore. If it's around 1.7 or 1.6, that's kind of that gray area. There are actually some bonds. I can show you them later. One of them is silicon dioxide. It's an awkward one, where silicon dioxide is actually supposed to be ionic, but it's really more covalent, actually, the way it works. Because its electronegativity difference is like right in that gray area. Okay. Anyways, once your electronegativity difference becomes smaller, which is like less than 1.6, you get to the point where you have polar molecules, but like they don't share the electrons equally, like say hydrogen and chlorine. Hydrogen is 2.2, chlorine is 3.2, something like that. What's the difference between 2.2 and 3.2? 1. Okay. So is there a winner to this fight? Yeah, but it's not a knockout. This was a knockout. This one right here, chlorine wins on points. But because of that, hydrogen and chlorine can stick to other hydrogen and chlorines. The spectrum continues, though, until you get to the point where you have no electronegativity difference, where you have exactly equal sharing of electrons, like, say, hydrogen with hydrogen. If you have two identical things with each other, then nobody wins that fight. So now you have this range of bonding. And depending on where your bond fits within that range, depends on the type of matter you have. Again, I'm specifically talking today about whether you have solids versus liquids versus gases. if you had completely non-polar molecules, what kind of state of matter would you expect? Yeah. If you had, as you go along the spectrum, and you start to get some polar bonds being formed, you're eventually expecting to find some liquids. And if you have ionic stuff is actually solid. That makes sense. Now, do keep in mind, though, solid bonds are actually not the strongest, though. This is kind of awkward. But the bond right here between these two hydrogens right here, this bond right here, the bond inside of a gas is actually very strong. The bond holding NaCl together is actually not strong. You can break it by just adding water. Does that make sense? So even though it's a solid, it may not actually have the most stable bond of all of them. It just happens to be in a solid format. Okay, here's another slide that's kind of important here. In order to figure out whether something is polar then, it's all about symmetry. If you have a nice symmetrical molecule, it may be nonpolar still. Like, for example, methane. I'll draw methane real quick one more time. It was C to C to H to H to H. And what happens is every single one of these fights is won by carbon. But because methane is symmetrical, it's a nonpolar molecule still. Does that make sense? Make one slight change. Make it ammonia. N lone pair to H to H to H. Same thing happens. Nitrogen wins all the fights, but see how this guy had a hydrogen pushing down from the top? This one right here doesn't have that fourth one pushing down from the top. This one is then a non-polar molecule. This one here is a polar molecule, explaining why this is a gas and why this is a liquid. Any questions? Okay, I've taught you a lot over the last couple of days. Here's what you guys need to do now. You need to practice this. So I've got 3 ways you can practice. First way, I'm going to skip ahead. I put in some slides in your notes here, which have a whole bunch of molecules that you can then start to practice drawing. Okay? It either gives you the name, it gives you the formula, or it might give you the dot diagram or the structural formula. Start practicing drawing diagrams. Okay, that's the first thing you can do. The second thing you can do is I'm going to send you guys an email link to a copy of this software right here. Okay. Tomorrow I'll give you a list of compounds. If you guys haven't seen the way the lab works, I'll show you real quick here because I've got a few minutes left. Let's see. Chemistry 20, chemical bonding, lab. So the lab that you're going to do is all done using the computer program. Okay. What I'm going to do is I'm going to give you 10 molecules, and I'll give you the list tomorrow because I got to look up which 10 they are. And what I'm going to have you do is, here's the procedure. Open the JMOL software, click on File, which is, by the way, up here. Go down to Get Molecule, and all you got to do is type in the name. Okay, so currently it's on methanol. Just type in the name. It will give you the molecule. Here's what I want you guys to do. Down below, I want you guys to write the molecule name, tell me the chemical formula. I want you to draw it in 3 dimensions. And I want you to tell me the shape of the atoms. So like tetrahedral, linear, bent. Does that make sense? I do want you to use color though, please. If you don't use a pencil crayon, at least do something to illustrate that, like, you know, like on this one here, how hydrogens are all white, carbon is gray, and oxygen is red. You use a color of some type. Okay, that's the lab, essentially. I want you to draw molecules and just practice this. Okay, I've actually more or less taught you the entire unit. Okay, we have one more lesson left. We'll do it after Christmas, though. But for the most part, we've actually covered everything. So, sound good? Okay, you guys may as well take off because it's basically time to go. But tomorrow I'll give you guys a work day, and you can start working on either the assignment, the lab, or practice stuff, I guess. Or you can finish up your test, too, I guess.